Warm welcome to yet another discussion on GATE Electronics and Communication Network related paper. Today we are checking GATE 2019. Moving to the first question, a fully charged mobile phone with a 12 volt battery is good for a 10-minute talk time. Assume that during the talk time the battery delivers a constant current of 2 amperes and its voltage drops linearly from 12 volt to 10 volt as shown in the figure. How much does the battery deliver during this talk time? Right. So we have to calculate the energy delivered by the battery during this talk time. Right. We know energy equal to power into time. Right. Here power equal to VI. Right. That means energy turns out to be 0 to t VI dt. Right, but I is a constant one because it delivers a constant current of 2 ampere. Right, so I am taking 2 outside. So integral 0 to t v dt. But v of t is as given in the graph. That means 2 into area of v of t. Right, 2 into area of v of t. So I can split this area into 2 halves. That means 2 into first one a rectangular part, that means a 10 volt into 10 minutes. 10 minutes converting to seconds, 10 into 60. Plus it's a triangle. So half into A. A is 2 into 10 into 60. Right? Half into 2. 2 is 12 minus 10 into 10. 10 is 10 minutes converting to seconds. That is into 60. Right? So that turns out to be 10 into 10, 100, 100 into 60, 6,000, 6,000 into 2, 12,000. So 12,000 plus 2 cancel, 10 into 60, 600 into 2. 600 into 2 is 1,200. So the answer is 13.2 kilojoules. Right? So option C, 13.2 kilojoules. Now moving to another one mark question. In the interconnection of ideal sources shown in the figure, it is known that the 60 volt source is absorbing power. Then which of the following can be the value of the current source I? Right? So only one hint is given. It is known that the 60 volt source is absorbing power. As it is absorbing power, current must enter to this 60 volt. Right? Now we can apply Kirchhoff's current law at this point. So this is that node. I ampere current is leaving as mentioned in the question. Now in the 60 volt case also another current is leaving from the node and I am marking it as IA. And this current, right, coming from this direction is 12. So it is 12. From that we have to evaluate current I. Which of the following can be the value of the current source I? That is I plus IA equal to 12 or I equal to 12 minus IA. Right? So that means that answer must be lesser than 12. Right? So checking the options, option A is the correct one. As option B, option C and option D are all greater than 12. So answer is A. And in the question it is mentioned as which of the following can be the value of the current source I. So it must be 10 ampere. That's right. So now moving to another one more question. If the transfer function of the following network is V naught S by Vi of S equal to 1 by 2 plus SCR, then the value of the load resistance RL is. Right? So we have to calculate the transfer function first of all for this network and have to equate it to this expression to find the value of load resistance RL. Right? Here there is an RL parallel, right? RL parallel capacitance combination is there. So first of all we have to evaluate what is the impedance offered by this RL parallel C. That is RL into 1 by SC divided by 1 by SC plus RL. So that is RL divided by 1 plus SC RL. Right? So that is the impedance offered by this part. Now we can calculate what is V naught S by Vi of S. So that is V naught S by V I of S equal to V naught S is the voltage dropped across this parallel combination. So current is I of S. I am marking current as I of S. I of S into this result, that is RL divided by 1 plus SC RL, right? All divided by, again, input voltage is the voltage drop across this R and the combination of this impedance. That is, again, current remains same as it is in series connection. So I of S into R plus RL by 1 plus SC RL, right? I of S and I of S cancel. That means RL divided by, I am multiplying 1 plus SCRL to here. So that is R plus SCRRL plus RL, right? Now I am dividing both numerator and denominator by RL. So 1 divided by R by RL plus SCR, right, plus 1. But it is given as 1 by 2 plus SCR in the question. That is 1 by 2 plus SCR. Now comparing these expressions, R by RL, right, R by RL plus 1 equal to 2, or I can write R by RL equal to 1. That means R equal to RL. So option C satisfies this. That is RL equal to R. Now moving to a 2-mark question. Given that f of s is the one-sided Laplace transform of f of t, then the Laplace transform of integral 0 to t f of tau d tau is, right? So it's a very direct question. If f of t is the Laplace transform of f of s, then integral 0 to t f of tau d tau equal to f of s by s, right? So answer is B. Now moving to another 2-mark question. An AC source of RMS voltage 20 volt with an internal impedance ZS equal to 1 plus 2j ohms feeds a load of impedance ZL equal to 7 plus 4j ohm as in the figure. The reactive power consumed by the load is, right? So we have to evaluate the reactive power. Reactive power is given as reactive power equal to VL IL star or IL complex, right? That is, we can substitute VL as ZL IL. So ZL IL into IL star, right? That is ZL into IL star is IL square or mod IL square, right? So first of all we have to evaluate what is IL, right? ZL is given, so we have to evaluate IL. Now we can evaluate IL. IL equal to voltage is 20 divided by total impedance, that is 1 plus 2j plus 7 plus 4j, that is 8 plus 6j, right? 8 plus 6j. Now we can substitute the value to this expression, that is reactive power equal to ZL is 7 plus 4j into modulus of 20 by 80 plus 6j. And the square of it, right, that is 7 plus 4j into modulus of 20 is 20 divided by square root of 8 square is 64 plus 6 square is 36, right? So 7 plus 4j into 20 divided by square root of 100, that is 20 by 10, that is 2, and is 2 square. So answer is 28 plus 16j. So now the reactive power, that is this term, is option B, that is 16 VAR. Moving to another 2-mark question. The switch in the circuit shown was on position A for a long time and is moved to position B at time t equal to 0. The current I of t for t greater than 0 is given by, right? So initially switch is at A and it attains steady state too, right? And at t equal to 0 switch is moved to B and we have to evaluate the current flowing through this 5 kilo ohm resistor after it is moved to B. Here there is a series and parallel combination of capacitors. So first of all we have to evaluate what is the net capacitance. So checking the capacitance, 0.2 microfarad is in series with 0.5 parallel 0.3, right? So 0.5 parallel 0.3 is 0.8, 0.8 is in series with 0.2. So that is 0.8 into 0.2 divided by 0.8 plus 0.2. So that is 0.16 microfarad capacitance is the total capacitance, right? Now we have to calculate what will be the initial steady state voltage value across the capacitance. So there is a 100 volt here plus negative 100. Now a resistance of 10 kilo ohm is there and the capacitors attain open circuit during steady state condition. So the voltage across the capacitors is 100 volt itself. So the initial value across the capacitors is 100 volt, right? Similarly, we can check what will be the final value. As there is no voltage sources during the time when switch is moved to position B. So final value turns out to be 0, right? Now we can use capacitor charging discharging expression, that is VC of t equal to V final minus V final minus V initial e raised to minus AT. For that I have to evaluate A. A equal to 1 by time constant equal to 1 by time constant is RC combination. So R is 5 into 10 raised to 3. C is as obtained 0.16 microfarad. So 10 raised to 6 on numerator side. That is 10 raised to 6 cancelled by 10 raised to 3. So on numerator side 10 raised to 3 divided by 5 into 0.16, that is 0.8. 1000 by 0.8, that is 1250. 1250 is the actual A. Now we can substitute all those values. V final is 0. So 0 minus again 0 minus initial value is 100. E raised to minus 1250 t, right? But this is the capacitor voltage, right? And we have to evaluate the current flowing through this path. So I have to use the expression I equal to C into dV by dt to evaluate the current flowing through the capacitance. As it is series with this resistance, the same current must flow through 5 kilo ohm also. So I equal to C into dV by dt. Now C is 0.16 microfarad. So 0.16 into 10 raised to minus 6 into derivative of this thing. That is 100 into minus 1250, right? Minus 1250 e raised to minus 1250 t. So that is equal to 0.16 into 100, that is 16 into minus 1250 into e raised to minus 1250 t into 10 raised to 6, 10 raised to minus 6 here. So 16 into 1250 is minus 20,000 or 20 into 10 raised to 3 e raised to minus 1250 t into 10 raised to minus 6 ampere. So the final answer is 20 e raised to minus 1250 t milliampere, right? As I have cancelled 10 raised to 3 with the 10 raised to minus 6 to give milliampere. Now the sign is minus 1, but the capacitor charging discharging is in opposite direction and the current turns out to be 20 e raised to minus 1250 t, right? The current flowing in this direction is 20 e raised to minus 1250 t. So option P. Now moving to another 2-mark question. In the circuit shown, what value of RL maximize the power delivered to RL? So here we have to evaluate Thevenin resistance. Thevenin resistance is the resistance obtained at this point AB when the points AB is open circuited. For calculating Thevenin resistance, I am evaluating open circuit voltage by short circuit current to obtain Thevenin resistance, which is the resistance which actually maximizes the power delivered to this load also, right? So first of all we can evaluate what is the open circuit voltage, VOC, right? Looking from this terminals AB, apart from this 100 volt, no other independent sources are there. So the voltage contributed by this part is 0. So the open circuit voltage at AB is 100 volt itself. Right? So I am marking directly, here it is plus, here it is negative. So the contribution by this part is 0 volt. As there is no independent sources associated with this branch, the net voltage contributed by this part is 0. So 0 plus 100 volt, that is open circuit voltage equal to 100 volt itself. Now we have to evaluate what is short circuit current, ISC. For that purpose I am drawing figure here. Right, I am short circuited the load part, that is RL is shorted. Now the circuit looks like this. This is A and this is B. Right, now we have to calculate the current flowing through this path. We have to calculate the current flowing through this path. Right, now voltage across these 2 points is, right, I am marking these 2 points as PQ. Voltage across PQ equal to 100 volt, right, as it is parallelly connected with 100 volt. Now we can evaluate what is the current flowing through this path. Right, current flowing through this path, that is 100 by 8. Right, 100 by 8 or 50 by 4 ampere current is actually flowing through this path. Right, now as current flowing through this path is 50 by 4, Vx turns out to be, right, Vx turns out to be, Vx equal to, current is 50 by 4, resistance is 4, so Vx is 50 volt. Vx equal to 50 volt. That means here there is a 50 volt dependent source is there. Now we can calculate what is the current flowing through this arm, right, this arm. So current flowing through that arm is 100 volt is here, 50 volt is here. So 100 minus 50, 50 by 4 current is actually flowing here also. Now we have to evaluate what is the current flowing through this direction. So current flowing through this direction is 50 by 4 plus 50 by 4, that is 50 by 2. Entering current equal to leaving current. So the net current flowing through this direction is 50 by 2. That means the short circuited current is obtained as 50 by 2. Right. So ISC equal to 50 by 2 or 25 ampere. Now we can calculate Thevenin resistance. Thevenin resistance equal to open circuit voltage is calculated as 100. Now short circuit current is obtained as 25. So Thevenin resistance is 4 ohm. Answer C, 4 ohm. Moving to another 2-mark question. The time domain behavior of an RL circuit is represented by L into di by dt plus Ri equal to V0 into 1 plus B e raised to minus RT by L sin t u of t. For an initial current of I0 equal to V0 by R, the steady state value of the current is given by. Right. So this is basically a RL circuit which consists of both steady state part and transient part. Right. So steady state part is V0 u of t. Transient part equal to V0 u of t into B e raised to minus RT by L sin t. Right. So here initial current is given. Initial current is I0 equal to V0 by R. We have to calculate the steady state value of the current. Steady state voltage is V0 by V0 u of t. So the steady state current is I of t equal to that voltage V0 divided by resistance. So answer is A. From theoretical part we know that during steady state condition the transients completely decay out and only the steady state part will be there. So at t tending to infinity that steady state contribution is given by I of t is V0 by R. Now moving to a 2-mark question. In the circuit shown below, the diode is ideal. The voltage V is given by. Right. So here we have to evaluate the voltage V and it is mentioned as diode is ideal. Right. So checking options are in terms of this voltage Vi. Right. And we have to evaluate this voltage V. So I am varying Vi for different cases and we can try which option satisfy it. I think this is the most easiest way to approach this type of problems. So suppose I am making VI equal to 0 volt. Now VI equal to 0 volt, the circuit turns out to be in this way. there is a 1 ohm resistance here plus negative V. Now only the 1 ampere current is the source in this circuit. That means the diode is short circuited. As the diode is ideal one, the diode turns out to be a short circuit. Now the voltage source has a 0 volt. That means it is also short circuited one. So the circuit turns out to be it in this way. Right, a 1 ampere is there. Now the voltage across V is V equal to 0 volt. Right. So checking options, minimum of Vi, 1. First option is minimum of Vi, 1. Now the voltage is 0 volt. So minimum of Vi, 1. That may be an answer, right? So A may be an answer. Now checking B, option B, maximum of Vi, 1. Now Vi is 0 and maximum of Vi, 1 is 1. So that may not be an answer, right? So now checking option C, minimum of minus Vi, 1. Minimum of minus 0 or minimum of 0, 1. That is 0. That may also be an answer, right? Now checking option D, maximum of minus Vi, 1. That is maximum of 0, 1. Maximum of 0, 1 is 1, and that is not the case here. So D is not also an answer. Now we have to evaluate which one, A or C. Now we can apply Vi equal to 10 volt. So the figure turns out to be V plus minus 1 ohm. Here there is 10 volt. Right. Now a 1 ohm resistance is here and a 1 ampere current is flowing. Diode turns out to be open circuited. Why? Because the voltage drop across a diode is positive here, negative here from the left part, right? Similarly, positive, negative here from the right part. That is, the voltage across 1 ohm is plus negative 1 volt and the voltage across this current source. So anyway, the diode must be open circuited, right? Now we can evaluate what is the voltage across V. So that is nothing but it is voltage across V equal to current flowing through this is 1 ampere. So 1 into 1 volt, right? 1 ampere current is flowing through this circuit. So 1 volt is dropped here, 1 volt is dropped here. Now the voltage across 1 ampere is actually 8 volt. Balance of the 10 volt, that is 8 volt is dropped across 1 ampere. Now we have to evaluate which one of the option A or C is correct. So option A indicates minimum of Vi, 1. So minimum of Vi, 1. That may be an answer because we obtained V as 1 volt. Now option C is minimum of minus 1, 1. Minimum of minus 1, 1 is minus 1, right? So option C is not also an answer. Therefore option A is the answer, right? Minimum of Vi, 1. So for more GATE tutorials, subscribe my channel. Now I am signing out till we meet again with another GATE paper. Thank you.